In chapter one, you start off with nice words, everybody's smiling at each other. You're talking about definitions and words, things like that. Um, no extremely difficult homework problems to work on. And then you start dealing with units and computational details. And you do start learning very quickly that the devil is in the details in terms of problem solving, particularly engineering problem solving. So I want to spend some time on this potentially a lot of details related to units and keeping units straight. So let's start digging in to working with both English and SI systems of units. So I hope that this module on units gives you some practice, some guidance, some example problems. Some of these example problems, a couple of them can get a little tedious. So hang in there, have a look at the kind of examples I give you, and this might help you in solving even some of your early homework problems. Remember in the last video had to do with properties, states, and processes, and I put the big important stamp on it. Well, I've got to do exactly the same thing on this video as well. It is so important to learn how to work with units. Working with units, canceling units, keeping units consistent are absolutely critical to your success in this class. Simply being good at number crunching is not enough. You've got to be able to write down in pencil and paper units and keep your units straight. That is simply a part of engineering, whether you like it or not. I have 3 videos out there on my Jay's Toolbox YouTube channels that you might want to look at. And so if you go to the Thermodynamics Fundamentals playlist and or the ME Prep playlist, you'll find 3 videos. So working with units, and then I thought, man, I did a great job on that. And then I discovered as time went by, a lot of students were having trouble with kinetic energy units and also canceling their units. So I created yet another even longer video. Look at this. This one's 43 minutes, talking more and more and more about how do you keep units straight with kinetic energy in terms of other energy units, keeping them all consistent. And another one of my videos, only 17 minutes long, is some basics about canceling out your units. And so it's some guidance that I hope might help those of you who have trouble keeping your units straight. And that's going to be covered a little bit in this particular video as well. Okay, so let's just work through certain properties a little by little. Units of mass. What's the primary dimension in our engineering world in SI units? Well, the primary dimension for mass is kilograms. And all you need to remember here, 1 kilogram is equal to 1,000 grams, and that's easy to remember. Over on the English side, the primary dimension for mass is the pound mass that I'm saying in words. And notice that I'm writing out LBM. And in my yellow text box, I want to point out right from the start, the text box, the textbook uses the unit LB. When you see in the textbook LB, I want you to always think LBM, pounds mass. So recognize the textbook uses the unit LB to represent a mass, not a force. Okay. And so in order to maintain your sanity, if you're mimicking things out of the book, if you're copying things out of the book, don't just blindly copy. When you see the unit LB, write out in your work LBM. That's what I do. And that enables me to maintain my sanity in thermal systems work, both as a student and practicing engineer. I'm not kidding. LBM, that's my strong recommendation. Okay, now as we work between SI and English units, which sometimes you will need to do, recognize that 1 lbm, 1 pound mass, equals 0.454 kilograms, or in other words, more familiar to you, 1 pound of mass equals 454 grams of mass. And so this is not weight to weight, it's mass to mass. 1 pound mass is 454 grams. And I bet you have that in your head, right? Because you buy things at Kroger and you convert, you look at grams and you convert over to pounds. What's units of length? What do we use length for? Distance, position. Um, it's the start. It's the numerator of velocity, things like that. In SI, of course, the primary dimension is meter, and of course, you know that 1 meter is 100 centimeters. You go from there. In English units, the primary dimension is feet, FT. You know through your own practical experience, 1 foot equals 12 inches. So that's like a conversion factor, isn't it? Another one that you may or may not have in your head is 1 mile equals 5,280 feet. I had to memorize that in fifth grade. Uh, you maybe not, but that can be important to you. It's going to be in your conversion factor in your book, I think. But that's going to be convenient when velocities are expressed in miles per hour and you need to convert to feet per second. Okay, when we're straddling the line, when we're converting feet to meters and meters to feet, recognize that 1 foot is 0.3048 meters. And then, of course, we take the reciprocal of that. 1 meter is 3.28 feet. And so in my world, I think of a meter as about a yard. So when I'm visualizing things, when I have engineering problems, when I hear about the 400-meter relay, 400-meter track, I'm thinking about that's around 400 yards. I know there's some difference, but a meter is about a yard. Units of time. Of course, time is a primary dimension in engineering, and you won't go wrong if you use your primary units of seconds. And again, you just want there's 60 seconds in a minute, of course. There's 3,600 seconds in an hour. You can figure that out on your own. I worked in a manufacturing facility that operated 24/7. We manufactured paperboard product 24 hours a day. And so part of my job was to analyze what did we do during each minute of the day. And so I quickly learned when I got my job, I quickly learned that there's 1,440 minutes in a day. Well, how did I get that? I knew that there's 24 hours in a day and 60 minutes in an hour. 1,440 minutes in a day. Now we're going to move on to force because quickly you're going to be faced with piston and cylinder problems. You're going to be doing engineering calculations, and you're going to be interested in free body diagrams, and so you're going to be balancing forces. You're also going to be calculating the weight of things, which is a force, right? So the weight of an object is the force with which the Earth pulls on that object. Okay, so weight is a force, isn't it? So force is not a primary dimension. So please recognize this. So for thermodynamics problems, force is not a primary dimension. So let's look at what are the units of force in both SI and English, recognizing that a force is not a primary unit. All right, so a force in SI is a Newton, N, 1 N. And a Newton is 1 kilogram meter per second squared. In other words, if you have a mass of 1 kilogram and it is accelerating at 1 meter per second squared, then the equivalent force is 1 Newton. A Newton is a kilogram meter per second squared. You need to commit that to memory. So I'm sorry, you got to get that in your head. So just simply putting that on a formula sheet is not going to help you win the day, is not going to help you perform well. In English units, The units of force are pounds force, lbf. That is incredibly important. Not lb, that's mass. In the textbook, you must write out lbf to document that you're looking at a force, not a mass. And then, of course, to straddle these things, I've written down these conversions, and we'll talk more about these for that one-page conversion factors page that you must find in your textbook. All right, so important part here is force is not a primary dimension in our system of units, and in English system, LBF is an expression of a force or a weight. Units of pressure. We've dabbled in this, haven't we? We've dabbled in this in a previous video module. Remember, pressure is a force acting uniformly over an area. Pressure is a property, okay? And so in SI units, so obviously pressure is not a primary dimension like mass, length, and time. Those are the three primary dimensions. So what's a pressure in SI? That's a Pascal. A Pascal, you must commit to memory, a Pascal is a Newton per square meter. If I multiply both sides of this expression by 1,000, I've got 1,000 pascals equals 1 kPa. And that's what you're going to be working with in this class, kPa. Another measure of pressure you're going to be working with is MPa. That's megapascals. I should have capitalized P there. 1 megapascal is 1,000 kPa. Consistent with what you know about the SI, the really cool nature of the SI, where you've got mega and kilo and things like that. Another thing that's important that you should commit to memory is that a bar is a measure of pressure. A bar is 100 kPa. And then another thing to remember is an atmosphere. That's another measure of pressure. That's 101 kPa, 101 and change. But basically, for us engineers, one atmosphere is 101 kPa. Recommend that one bar is 100 kPa. And so do you see that one bar pressure-wise is about one atmosphere, but not exactly equal to one atmosphere? Okay, ATM, it's pronounced atmosphere. Let's go over to English side. Pounds force per square inch is the unit of pressure in English. Pounds force per square inch. And in shortcut, we call that PSI. So 1 pound force per square inch. It can be written 1 PSI. And then recognize, let's see, how would I convert pounds per square inch into pounds force per square foot? I would do my conversion, can just about do it in my head, okay, thinking that, let's see, how many inches squares would I need to make up a 1 foot square? I'd need 144 1-inch squares to make up 1 square foot. And so that's how I can visualize that 1 pound per square inch is 144 pounds force per square foot. Okay, we're working through our various properties. Temperature. We've covered this in a video already, haven't we? So remember that you should be able to, I did a terrible job of explaining how to get this into your head. If you take 9/5 times degrees C and add 32 to it, that gives you degrees F. So boiling point, remember 100, if I take 9/5 of 100, add 32 to it, that gives me 212, okay, degrees C. If I take 212 degrees F, boiling point, subtract 32 from it, I get 180, and take 5/9 of it, I get 100 degrees C. So I can derive these two conversion relationships from my head. Absolute temperature units, it is worth repeating. You're going to be working in absolute temperature most of the time in this class, degrees Kelvin or degrees Rankine in the English system of units. So if you're given degrees C, you add the number 273 to it, degrees K. If you're given degrees F, you add 460 to it to get degrees R. And the author in the textbook does a nice job of giving you some rationale for why do I just add 273 instead of just being given the number like I'm doing. The author of the textbook does a nice job of explaining how come you add 273 degrees C and how come you add 460 degrees F to get absolute temperature. So we'll leave it there. But functionally, that helps you understand what you need to do to start solving homework problems that involve temperature. Okay, units of energy. There was another module on this. Okay. We talked about there's potential energy, kinetic energy, internal energy. So all of those are a property. They have things in common. And so in terms of the extensive property energy in SI units, the unit is a joule. A joule. Wow, what's that? Well, you do have to remember, you do have to remember that a joule, the definition of one joule is 1 Newton meter. 1 Newton meter. That's the definition of a joule. Okay. So if you bust out a Newton, what's a Newton? You'll see that a Newton is a kilogram meter per second squared times meters. And so this is not a typo. 1 joule is 1 kilogram meter square per second squared. Right. We're just going to leave it at that. Over on English units, units of energy is foot-pounds force. Okay. Also, like I told you, BTUs, a British thermal unit, is also a measure of energy. My dad tried to explain it to me in high school, and I just wasn't getting it. But by golly, I learned what a BTU is when I started taking my first course in thermodynamics. And the relationship between a BTU, a British thermal unit, and a foot-pound force is this expression. And you're just going to have to commit. I'll have to apologize and say you got to commit this to memory for speed and doing your homework, quizzes, and tests. 778 foot-pounds force equals 1 BTU. You got to get that into your head. 778 foot-pounds force is 1 BTU. Okay, so anyway, that's make a mental note to get that into your head. That'll save you a tremendous amount of time in problem solving in this class. And now a trick I learned at Virginia Tech. I can't remember exactly when I learned that, but I believe I learned it when I was early in my sophomore year. And then I reprised back to the 7th grade. And I remember my 7th grade math teacher talking about what at the time we thought was dumb, that you can take any algebraic expression, x plus 5, and multiply it by 1 and preserve that expression. It's x plus 5. And boy, in 7th grade, we'd laugh, kind of make fun of that because that's obvious. And then I started putting 2 and 2 together to see that that has some value. So remember, you can multiply any algebraic expression by unity and preserve that expression. That's the key. So for example, how many inches are in 1.75 feet? Now, you know in your head that you multiply 1.75 by 12 to get inches. So that comes naturally to you. But let me take you through my little unity trick so you'll see how to do it. I'm going to write down what I've got, 1.75 feet. And then I'm going to multiply that by unity. And I know off the top of my head that unity can be expressed as 12 inches in the numerator divided by 1 foot in the denominator. And when I write this out in pencil and paper, I can cancel with my pencil. I can strike out feet in the numerator and feet in the denominator and get 21 inches. That's how you do that. Okay. So I appreciate that you know automatically to multiply 1.75 by 12 to get the answer. Get this in your eyes. Think about this because these problems get much, much, much harder. And if you can master this kind of unity trick, it's going to pay off for you in spades as you go along in problem solving on your homework, in quizzes, and tests. Okay, another example. How many meters in 1.75 feet? So that's going to be a little tougher, isn't it, to just know off the top of your head what to do. You're going to look, so here's our 1.75 feet, but we need to figure out an answer in meters. So we're going to go and look up a conversion factor I haven't memorized this. I have to go look up this conversion factor every time. Okay. 0.3048 meters equals 1 foot. And so that's how I generate unity. So numerator 0.3048 meters, denominator 1 foot. I write it down on pencil paper, strike out my units to get, and do the math with my calculator, 0.533 meters. So that's the way to get to the answer. And does it make sense? Well, I know that 3 feet is about a yard. Okay. And so, yeah, this makes sense, 0.53. So, yeah, that's kind of making some sense. You got to be able to find this. I've been harping on this, I think, in previous videos, maybe. If not, future videos. You got to be able to find this one-page conversion factors page in your textbook. You need to figure out how to get it into a PDF format or print it out on a hard piece of paper and possess this thing, either electronically by PDF or a piece of paper. Don't just keep going back online to to find some link or something like that. That's going to be a killer for you in the time you spend on your homework, and you got to have some conversion factor, either piece of paper, when you're working on your quizzes and tests. So anyway, this gives you the visibility of where I got that conversion factor out of your one-page conversion factors in the textbook. Very nicely arranged. I was delighted when I came back and started teaching the class and saw this one page. It was very nicely done, very nicely arranged. Okay, we're going to go through a couple of example problems that have confounded students over and over again. Example 1 is easy. Example 2 is, I'd say, much harder. Example 1 is SI. Example 2 is going to be English. A person has a mass of 68 kilograms given. What is the person's weight on the earth? And that's all that's given to you. Can you think about how you'd solve this problem before we go to the solution? Person has a mass. You're on the earth. What's the person's weight in SI? Now, well, what's the desired answer? What units are you going to express your answer in? Newtons. It's not mentioned in the problem statement, is it? You got to know that as an engineer. I need to express my answer in newtons. Okay, here we go. So we know that, well, you say, well, I know the formula. Well, this is a little more than a formula. It's an expression of a person's weight on Earth or anywhere, as long as you know G, is the mass times the acceleration due to gravity. It's more than a formula. We also know as engineers that if we're on the Earth, G is 9.8 meters per second squared. So W equals mg. Let's go through as if we were writing it on pencil and paper. 68 kilograms times 9.8 meters per second squared. That equals, we do the math, 666.4 kilogram meters per second squared. I've got to recognize that this set of units, a kilogram meter per second squared, that's a Newton. So I've got to keep writing. I can't just leave it here. I've got to say the weight is 666.4 newtons. In my world as a practical engineer, I did more than simply circle an answer, even though this can work for you, okay? But notice here, the answer is more than 666.4. It's 666.4 newtons. Absolutely necessary to keep that written down. And I like to write out a sentence. A person with a mass of 68 kilograms weighs 666.4 newtons on Earth. Simple as that. Example 2, a person has a mass of 160 pounds mass. What is the person's weight on Earth? All right. What does your answer need to look like? What units do you need to express your answer in? You need to express your answer in pounds force, not LB, not the word pounds, LBF. Okay, here we go. All right, well, let's go through the drill as if just blindly. W equals mg, got it. G equals 32.2 feet per second squared on Earth. That's common sense. That's something you know off the top of your head. So if you're on Earth, G is about plus or minus a time, something in the fourth decimal place, 32.2 feet per second squared. Let's do the math. W equals mg. M, 160 pounds mass. G, 32.2 feet per second squared. We'll do calculator work 5152 and write out our units. Pounds, mass, feet per second squared. Trouble. Rather than being a smart aleck about it, I just want to come right out in a yellow text box and say 1 pound mass feet per second squared does not equal 1 pound force. Please be aware of that. Okay, many students think that yellow text box is green, and 1 pound mass feet per second squared does not equal 1 pound force. Many students think it does, and they lose lots of credit. Okay, so we need a units conversion. So we've got to keep working on this, because we can't just say that's our final answer and then, okay, grader or professor or instructor, you figure out the rest. That's a no-go. We've got to express our answer in pounds force. We need the units conversion. We're going to go to that one page, and we're going to look under in the force section, and we're going to discover this equivalency here. 1 pound force equals 32.174 lbm. Okay, remember what I lectured about in the textbook. You see lb? Keep your sanity, right? lbm. 32.174 lbm, pounds mass feet per second squared. That's unity. So unity, how do we form up unity? Well, we select one as the numerator and one as the denominator. I plan ahead. I said, I need units of force. So I'm going to select 1 pound force as my numerator. I'm going to select this as my denominator. I'm going to write this out on my page. I'm not going to take any shortcuts and say, I can do this in my head, because I'm going to suggest that you're lying to yourself if you think you can do this in your head. Anyway, try it if you wish, but you're not going to succeed. So if you write this out, pencil and paper, you've got pounds, mass, feet per second squared. You do some studying, and you see down in this denominator, you've got pounds, mass, feet per second squared. All three of these terms are going to cancel. And so now you're ending up with 1 pound force. So there's my unity trick that has paid off for me. And I will tell you that when I tried to do it in my head as a student, I failed miserably. So writing this out, and so I learned in practice that I still need to start writing this out. Okay. So anyway, the answer for us is, so we do our calculator work, 5152 divided by 32.174. We've got our units straight. And so our answer is the person weighs 160.1 pounds force. And so in my sentence, I'm going to say a person with a mass of 160 pounds mass weighs 160.1 pounds force on the earth. Not going to, and you say, wow, numerically that looks very similar. And I totally agree. 160 and 160.1 are very similar numerically, but I still want you to satisfy yourself. There are some subtle reasons why you must get good at this, because this is about as simple as an example as you can get. And the thermo problems get harder and harder because you're dealing with more and more complex relationships than W equals mg. Okay, we're going through now. We're continuing to go through and look at properties and units associated with properties. What's capital V? What's little v? You remember? Capital V is volume. Little v is specific volume. So you should have this in your head. So I'm trying to, here's U. Here are some formulas, but they're not really formulas, they're fundamentals. You learn little v is capital V over m. You got that? So you can derive this one, right? Multiply both sides by m. You remember also that density is 1 over specific volume equals mass over volume. Okay, so you only need to really write down one of these, and you've got it. And hopefully you've got most of this in your head. English units for the extensive property volume, cubic feet. SI units, cubic meters. Obvious. Little v, English, cubic feet per pound mass. SI units, cubic meters per kilogram. Pressure units. you're going to find that in homework problems, test problems, quiz problems, instructors and the author, they throw a mishmash of pressure units at you in the given problem statements. So you have to be able to work and transform all of these pressure units into the needed units. So you remember that pressure is force over area. So all of these pressure measurements are force over area. We talked about the difference between gauge pressure and absolute pressure. And look, in most textbook problems, once you get out of chapter 1, it's smooth sailing. Nearly all given pressures outside of chapter 1 are given in absolute pressure. So stay calm, don't panic. Most everything that's given in this class beyond chapter 1, maybe chapter 2, are absolute pressures. Okay, so pressure in English units, 1 psi, that's 1 pound force per square inch. Okay, we've covered this. 1 atmosphere is 14.7 pounds per square inch, pounds force per square inch. Let's see, it's got to be in here somewhere. There it is. There's the bottom one. Okay, so remember my unity trick. You're usually converting pounds per square inch, which it would be given in a problem statement. And it is very common that you need to transform your pressure into pounds force per square foot. So my unity trick, 1 equals 144 pounds force per square foot divided by 1 pound force per square inch. That's how you do that. SI units. Commit to memory that 1 bar is 100 kPa. There's some subtle reasons for doing this, and I'm going to show you this in just a minute. Okay, so in algebraic equations, you're nearly always converting bars, I'd say always, into kPa. Okay, nearly always. So in my unity trick, 100 kPa is 1 bar. So these two things are identical statements to each other. Okay. And so you say, what's with this bar thing anyway? It's not real familiar to me. I didn't learn this in high school. I didn't deal with bars anywhere in college chemistry. You say, well, why are we dealing with bars then in this textbook? And here's the reason. As you get into chapter 3, you're going to be going to the back of the book to various property tables. This example would be called steam tables. A little bit more on that later. But recognize the left-hand column. The units of the left-hand column are bars, I call it. Okay. And so in a problem statement, you might be given the pressure is 100 kPa, but you have to look up some numbers in bar. So that's why you have to quickly learn that 100 kPa is 1 bar. So 150 kPa would be 1.5 bars. And you'd look up in a different row. So that's how come we use bars, is because in the back of the book, we're using property tables where the pressure column is typically tabulated in bar. Well, that brings us up to maybe I can declare you an expert in dealing with units as it relates to properties, as it relates to working back and forth between English units and SI units. Okay. And so here's my recap. Consider adopting my multiply by unity practice in keeping units straight. There are other methods. Other instructors may suggest other methods. Please consider that. I want you to develop a method that works best for you. So it's not like my multiply by unity trick is the method, but it sure does work for me. It's worked for me for years. Find the 1-page conversion factor sheet, save it to a PDF file, print it out to a paper copy. Do both of those. Get good at both SI and English units, because you're going to be having a mix no matter what section you're in. I strongly believe that you're going to be having a mix of both SI and English units. Certainly there are instructors that might be 50-50. There may be some instructors that might go 90% SI and 10% English, but you will discover that as you go along. But okay, so maybe now I can declare you experts in units, um, units canceling, and keeping your units straight. It is going to pay off for you as you do get better and better at your problem solving in this class and beyond. So the next video up to finish up chapter 1 is a recap and some of my just some jabbery words where I try to encourage you to move on to chapter 2. I will try to explain how it does get harder and give you some ideas of what you need to do to keep working hard and in order to get a good grade in this class. Train yourself to be a practicing engineer in the future once you get out of undergraduate. You might choose to go to graduate school, and you get out of that and you start your practicing engineering. All right, I hope that helps. I may have gone on a little too long on all of these units, but it's such an important topic that at least you could, even if you just blaze through it or jump through certain things that you felt comfortable with, at least you've got a place you can come back to. If you get hung up on homework, if you get a bad grade on a quiz, you want to find out maybe why you got a bad grade on the quiz, because the quizzes help you prepare for the test. And so if you can figure out maybe what you need to do differently from your quiz performance, that's going to help you perform well in a test.